Morning or good evening to wherever you're watching, wherever you are. I am Gabriel Thornton. I'm presenting with Jasper and Carter on PH 212, and we chose the turntable problem. I'll be going through the description. So, starting off, here is the diagram of what we're given. We are given a mass of big M, which you can see here, on top of a turntable, and we know that the turntable is rotating. So, I can't really visualize, but the turntable will be moving horizontally this direction, not up and down, but across the plane. We have P for our pulley. We have our tension in our ropes, and we have our smaller mass here. Now, good thing to note is that our rope is wrapped many times around this mass here. This mass is not moving upwards or downwards. There is a force opposing it. And additionally, to this big mass here, this is not moving as well. And we have an ideal pulley and string, so there is no mass in this pulley. This does not need to be accounted for. And the mass in our smaller m here is hollow. So we know that there's nothing in between this. And it's good to note that there is a hollow point between this as well. So the string runs through the board and down around smaller m mass. And we have no, like I said, no shifting and no moving from any of these parts. Only position that is moving is our board rotating horizontally around our plane, around our y-axis. Yeah. And that is the kind of layout that we have so far.
Hello, my name is Carter, and I'll be doing the solution part of our project. So after drawing out a description of the project and two free body diagrams, so for each object, we identified that the normal force and the force of gravity acting on the big object will cancel each other out, and the net force on that object will be equal to the tension force. For the small ball, the net force will be the force of gravity minus the tension force acting on it. And these are going to be the only two forces. The tension force is acting on the edge of the ball, and the force of gravity will be acting on its center of mass, so the center of the object. We also identified a few equations that we're going to need to solve this problem. So for angular velocity and acceleration, the two equations for torque, the moment of inertia of a hollow sphere, as well as Newton's second law. So where we're going to start with this problem is that because it states the object, the turntable and the object on its edge are moving in uniform circular motion, so with a constant angular velocity, we're able to use this equation for the centripetal acceleration of an object in uniform circular motion. So we know that AC is v squared over r. And using what we know about the relationship between angular velocity and tangential velocity, we can rewrite this as the centripetal acceleration is WR squared over R. So RW squared. We also know that the net force acting on the object is equal to its mass times acceleration. So by rearranging this and solving for acceleration, we know that the acceleration acting on this object is equal to its net force divided by mass. And again, because the net force is equal to just the force of tension acting on this object moving in circular motion, we know that the tension force divided by the mass of the block is equal to RW squared. So to solve for the angular velocity, we need to solve first for the force of tension. And to do that, we're going to do a torque analysis on the ball. So using the two definitions of torque, we can write I alpha as 2/3 m little m r squared. And this is going to represent the moment of inertia of the ball. And it'll be times alpha. And this is going to equal r cross f, which will be rf sine theta. And because they're at a right angle, this will end up just being rf. So r times the force of tension. R times the force of tension. Another equation that we can get about the ball is that the net force acting on it is the sum of these two forces, or the difference between these two forces. So we can write that F net equals Fg minus Ft, which will be Fg is just mg. Mg minus Ft equals ma. And using these two equations, we'll be able to solve for the tension force. So rearranging this one and plugging in A for alpha, we know that alpha is A over R. So we can rewrite this as A over R, and canceling one of these R's, we'll just be left with A. And because there's an R on both sides, we can cancel those. And rearranging for A, we can get that A equals the force of tension times 3/2 M, 3 over 2 M. Plugging this into the equation that we have right above it, we can get that mg is equal to, and so bringing this tension force over the other side, so 2/2 the force of tension, and then it'll be plus 3/2 the force of tension. When we bring this over, this will cancel, so we have A here. If we multiply this by M, MA equals the force of tension over M. So MA equals FT over times 3/2. So we can replace this chunk here with what we have here and bring this over to the other side. We will have 5/2. The force of tension equals mg. So rearranging this to solve for the force of tension, we have that the tension force is equal to 2/5 little mg. So now that we found the tension force, we can plug that back into the equation we have up here, where the force of tension over the mass of the big block is equal to the radius of the big block. So this should be a capital R, times the angular velocity squared. So we have 2/5 mg equals rw squared. And rearranging this for angular velocity and taking the square root, we can get our solution that the angular velocity is equal to 2 mg over 5 mr. Again, where the capital M and capital R is the mass of the block and the radius of the turntable, and little m is the mass of the ball. And so this is what we have for the final angular velocity of the turntable and the block. And that's been the solution. Thank you.
All right. Now that we have our angular velocity equation, we have angular velocity omega is equal to the square root of small mass times gravity over big mass times big mass's radius, which is here, all times 2/5 in the root function. Now that we have that, we have to make sense of what we found. So what we got to do is first, we got to look at units to make sure the units make sense. First two units, big mass and little mass, they're both kilograms. Gravity is an acceleration, so it's meters per second squared, and radius is in meters. Now with these units, we can combine them all in the function to see if they match. So we'll take our kilograms times our meters per second squared, and we'll put that over our kilograms times meters. Now that we've put this together, we'll ignore the 2/5 because 2/5 are a constant. Take the root of all that. Now we can start canceling units. So the first thing we'll do is we'll cancel our kilograms. There's one on top, one on bottom. Next, we'll cancel our mass, or our meters, sorry. Cancel out our meters, and we'll be left with square root of 1 over second squared. Because remember, we have a divider on top, so that means that second squared is actually on the bottom. So we have 1 over second squared, square root that, and that'll give us 1 over seconds, which initially may look like it doesn't make sense, but then you remember that radians are a unitless measurement, so we actually get radians per second, which is the desired unit for angular velocity. Now that we know we have the right units, next what we have to do is make sure our equation itself actually makes sense. Because even if we have the right units, if it doesn't make sense, then it's still wrong. So what we're going to do is we're first going to look at the mass on top, little m here. So if this mass increases, we're talking down here, if this mass was all of a sudden really big, right? That means there's more of a tension force pulling down, right? There's more of a tension force pulling that mass inward, big M inward. When M gets pulled inward, that's our acceleration inward. So our acceleration inward is increasing, which means that we need to spin faster in order to stay on the outside. Otherwise, our mass will move inward. So increasing mass of the falling weight increases angular velocity, makes complete sense. Next, we'll look at big M on the bottom. If we increase the mass of our cube here on the turntable, it will be heavier, which means that the force will have a lower acceleration for the same amount of force, right? So if F equals ma, if we increase the mass, the acceleration will decrease, right? So that means that if we're increasing our mass, our angular velocity will have to get smaller because that acceleration will get smaller. And it's vice versa of the previous one, right? So if there's less acceleration inward, we need to go slower so that we don't go outward. And last thing, radius. If the radius is greater, although the angular velocity may stay the same, remember, angular velocity is related to translational velocity. So if we're increasing our radius, the angular velocity may stay the same, but the translational velocity will increase, which would shoot it off of our turntable unless we increase our acceleration inward. And since r is on the bottom, since r is on the bottom, we're increasing that distance. So as r gets bigger, we need the turntable to move slower so that this velocity doesn't increase. And that means we understand why our mass 1 is on top, our big mass is on bottom, and our radius is also on the bottom. So now that we know that all our units make sense, we can confirm that this equation does make sense.
Going to our reflection. So some similarities we could find are from looking at homework 4. In homework 4, we are also trying to find the angular speed of a system, but it's a little bit different. In both of these cases, we are solving for angular speed found from a system rotating horizontally. So that's another similarity we can see. Both of these are rotating horizontally and kind of have it going around that y-axis as said before. Some specific differences we can see. Unlike for homework 4, we have a mass that must be accounted for hanging from our turntable. So in this equation that we did here, we had to account for the string being around the mass pulling on the string pulling back down on the mass, and it going all the way back up to our bigger mass, the one that is not hollow. And additionally, we are finding a difference in angular speed. So with this system, we are not accounting for how it moved without the block and without the block, with the block and without the block, without the pulley, with having mass. But in homework 4, we had the angular speed initially of the turntable, and then we had to find it after adding a weight of mass to it. So that's the kind of difference we have. Where this system is already given to us, we just need to kind of put the formula in and go about doing it that sort of way. Yeah, and those are your main similarities and differences you can kind of find in those initial systems.